Now we will have a closer look on the synthesis of substituted benzenes. And most of the time, only one structural isomer is required, which can be very difficult to achieve. And therefore, it is important to take the following questions into account. So the first question is the substituent an activator or a deactivator? And does the substituent direct electrophile to the 2 and 4 or to the 3 position of the ring? Then we need to know how reactive is the electrophile and what are the reaction conditions, and are there any byproducts formed, or does the product react further? And we will now start with the reactivity and the choice of reaction conditions. Here we have the example of a bromination. And let's have a look on the bromination of nitrobenzene. If we have nitrobenzene, the nitro group is strongly deactivating, and therefore we need the Lewis acid in order to generate a stronger electrophile, which can then react in the electrophilic substitution in order to generate 1-bromo-3 nitrobenzene. And the reason for this is that the nitro group is strongly deactivating, and hence benzene will only react with a strong electrophile. Conversely, if we have a look on the bromination of phenol, then we can see that we do not need Lewis acid in order to generate a stronger nucleophile. So here, benzene can already react with weak electrophiles, as it is activated by this hydroxide group. To form 2,4,6-tribromophenol. And this is surprising, as we know that each bromide substituent is a deactivator. However, there you can see how strong the hydroxide group acts as activating group. So, in other words, although we have already one deactivating bromide substituent, the hydroxide group is a stronger activating group, and therefore the reaction towards the tribromophenol will proceed even without Lewis acid. Another example is shown here. Interestingly, neither nitrobenzene nor phenylamine react in Friedel-Crafts reactions. And the reason that these two molecules do not react in Friedel-Crafts reaction are different ones. Nitro group is a strong deactivating group. Therefore, the ring is too unreactive to react with a coordination complex, and therefore we cannot observe a Friedel-Crafts reaction. But for phenylamine, we have an activating group. So why does it not react in Friedel-Crafts reactions? The problem here is that the aluminum trichloride reacts preferred with the amino group in order to form a coordination complex. And hereby, the formed coordination complex has a positively charged nitrogen atom, which exerts a -I effect to the ring. And hence, the ring gets deactivated and does not react in Friedel-Crafts reaction. Let's continue with the formation of byproducts and further substitution. In an electrophilic substitution, usually a mixture of structural isomers is formed. For example, in the nitration of methylbenzene, we can see that there are 3 structural isomers resulting in different amounts. And as we just learned, the methyl group is a 2,4 directing activator, and therefore the nitronium ion is directed to the position 2 and 4 in the ring. That's why we expect to see these 2 structural isomers. Nevertheless, there is a very small amount of 3-nitromethylbenzene formed. And if you now want to isolate only one structural isomer, you can separate those as they have different physical properties, such as boiling point. So they can easily be separated by distillation. Other byproducts are formed by polysubstitutions. For example, again, the nitration of methylbenzene. So due to the 2,4 directing activator group, which is the methyl group, The nitration yields 2 or 4-methyl nitrobenzene. But as the nitro group has a strong electron withdrawing effect, the subsequent nitration becomes increasingly more difficult with increasing number of deactivating nitro groups. That means if we now have one nitro group already substituted, the following nitration will be more difficult. And here you can see that we already need higher temperatures. And if we now have two nitro groups already on the benzene ring, the third nitration is even more difficult. So that means if we want to synthesize TNT, reaction conditions are more forcing than for the nitration of methylbenzene. Only a limited range of electrophiles react with benzene in electrophilic substitution reactions. Accordingly, it is helpful to transform existing substituents in other functional groups. And such a transformation can, for example, be done by a redox reaction. As shown here, the Clemmensen reduction can be used in order to transform the ketone group into an alkyl group. And similar to this reduction, a nitrile group can be transformed into an amine group when using tin and hydrochloric acid. And these two reductions transform a deactivating substituent into an activating substituent. And another example is the oxidation of a methyl group into a carboxylic acid group. And this oxidation can be performed by using potassium permanganate. And hereby, the activating substituent is transformed into a deactivating substituent. And here you can see an overview of the possible substitutions of benzene. So as we already discussed, we can perform a halogenation of benzene. We induce a 2,4 directing deactivator. We can also perform a sulfonation, and then we know that the substituent is a 3-directing deactivator. If we do a Friedel-Crafts acylation, the substituent will be also a 3-directing deactivator, and then we can perform a reduction in order to generate a 2,4 directing activator. Conversely, if we perform a Friedel-Crafts alkylation, the substituent will be a 2,4 directing activator, and if we then oxidize the substituent, we generate a 3-directing deactivator. If we do a nitration, we have a 3-directing deactivator. However, if we then reduce, we end up with a 2,4 directing activator. Another transforming substituent is the diazonium ion. And herefore we have the reaction with a nitrosonium ion. And the nitrosonium ion is formed in situ by reacting with sodium nitrite and hydrochloric acid at 0 degrees. This in situ formed nitrosonium ion is a very strong electrophile and reacts with the nucleophilic amine at very low temperatures, so at 0 up to 5 degrees. And hereby, a new nitrogen-nitrogen bond is formed. After the subsequent deprotonation, a nitrous amine is formed, which then reacts in a series of protonation and deprotonations, leading to the formation of an aryl diazonium ion and water. And the aryl diazonium ions are very unstable, and on warming to room temperature or even above, they lose nitrogen, which is a very good leaving group. This forms a very unstable aryl cation that reacts with nucleophiles in SN1 reactions. And for example, the reaction with water introduces a hydroxide substituent on the benzene ring, which is an important way to synthesize phenols. So here you can see the wide range of substituents which can be introduced based on the reaction of an aryl diazonium ion. And if we start here, you can see 3 reactions with copper 1 salts. And these reactions are called Sandmeyer reactions. And here it is postulated that the reactions involve an aryl radical intermediate rather than an aryl cation. And besides these Sandmeyer reactions, we have other reactions in order to form substituted benzenes. As we now know, an activating group directs the electrophile to the position 2 and 4 on the benzene ring. And the ratio of the formed structural isomers depends on the size of the activating group. The larger the activating group, the greater the amount of the 1,4 substituted structural isomer. And for small activating groups, a relatively large amount of 1,2 substituted benzenes will result. And this is a problem if the 1,4 substituted benzenes are required. So to increase the selectivity for the attack of the electrophile in position 4 of benzene, the size of the activating group is temporarily increased. For example, the small amino group is a 2,4 directing activator. However, if a blocking group is introduced, the electrophile can selectively be directed to the position 4. Therefore, the small amino group is temporarily transformed into a large amide group. Then the electrophilic substitution is performed in order to yield selectively the 1,4 substituted benzene, and afterwards the amide group is converted back into the amino group by heating up in aqueous sodium hydroxide. And a very important property of such a blocking group is that it is easy to introduce and also easy to remove. And here are two more examples for a temporary substituent, namely the sulfonyl hydroxide and the amino group. And the trick here is to temporarily introduce a substituent which directs the electrophile to a certain position, and at the end we remove this temporary substituent, similar to a blocking group. So, for example, here, in the first example, we introduce the sulfonyl hydroxide group, which is a deactivating group, and therefore the electrophile will be selectively directed to the 3 position on the ring. And as you can see here, the nitro group will then end up in the 3 position according to the 3 deactivator. However, if we then have a look on the complete molecule, we can see that compared to the first substituent, the nitro group is in the 2 position. Hence, the last step will then be the removing step of this temporary substituent, and we end up with this 1,2 substituted benzene ring. And here, another example, we start with a benzene molecule. We introduce now an amino group, which is known to be an activator group. Accordingly, we can assume that the electrophiles will be directed to 2 and 4 position on the ring. So then we also need to consider the strength of this activating group, and we know that the amino group is a very strong activator, and therefore the bromination will take place on 2, 4, and 6 position of the ring. Afterwards, the last step is the removing of this temporary substituent, and we end up with the tri-substituted benzene ring. If we now want to synthesize polysubstituted benzenes, it is important to consider the directing effects of each substituent on the ring. For example, if we would like to synthesize this 1-bromo-3-nitrobenzene molecule, it is important that we consider the order of the reactions. So we start first with the nitration of benzene. Hereby we introduce a 3-directing nitro group. Then subsequently we can perform a bromination, and we will end up with this 1-bromo-3-nitrobenzene. Conversely, if bromide is introduced first, then we have a 2,4 directing substituent, and hence in the following nitration, the nitro group will end up in position 2 and 4 on the ring. Accordingly, it is not possible to synthesize 1-bromo-3-nitrobenzene if we start with the bromination first. So, and now also important, what happens if 2 substituents direct the electrophile to different positions on the ring? Then the more powerful activating group on the ring will control the position of the electrophile.